Hello friends. So in the previous video, we have concluded our discussion on the delta zigzag star connection. Okay, and we saw that the delta zigzag star has a similar phasor characteristics as compared to a star or a delta connection. That is, you can get a phase difference of 0 degree or 180 degree with various configurations of the delta zigzag star connection. So once we have discussed delta zigzag star, it is time to discuss the star zigzag star connection. Well, let us see what we find out regarding the star zigzag star connections. For that, first we have to draw the connections, and before that we have to just see how the circuit looks like. So star zigzag star, the primary is connected in star. In the last case it was delta. The secondary is connected in zigzag. Okay, it is connected in zigzag star. And what was zigzag star? You take one set of terminals and connect them in star. The other set you connect in subtractive polarity, right? So this is what we have discussed all around in the delta zigzag star connection. So basically the only change will be in the primary side. We are going to just connect it into star. So how do you are going to connect it into star? I'll take the non dotted ends and I'll connect them together because that is the star connection, right? I'll put a neutral point here. So this is the star connection in the primary side. And how do you do the zigzag connection? Now the zigzag connection, as we usually do, what do? We take one terminal here, right? So we take one terminal here. Let us take A1, B1 and C1 and let us connect them in star, right? So this is connected in star now, like, so this is going to be the neutral point. And then you have to connect them in subtractive polarity. So A2 will connect to B4, B2 will connect to C4 and C2 will connect to A4, right? The undotted ends of the different windings are connected together. So this is one connection, subtractive polarity. This is the other connection, subtractive polarity. This is the third connection for the subtractive polarity. And now we are going to take the outputs across A3, B3, C3. Sorry, I am having a small throat problem here, so please excuse me for that. So this is basically the connection. Now the inputs we are going to apply here, that is, this will be VA, this will be VB and this will be VC. Balanced three-phase connections we are going to apply here, and VA will be V angle 0, VB will be V angle minus 120 and VC will be equal to V angle minus 240 degrees, right? So this will be having the ABC phase sequence. These are things very important. That's why I always stress this in all the videos, right? So if you want to just write down the line and phase values here, so the line voltage will be the voltage between two phases. So this is VLP, and the phase voltage will be the voltage across a coil. So I can just write this voltage here. So this A1 with respect to neutral will be the phase voltage. So this is V phase in the primary side. And as compared to a normal connection, I told you the zigzag connection is a little bit different. So here, this will be the phase voltage, which, for example, let us take the A terminal. So the phase voltage will be from this terminal to the neutral, right? So this will be the phase of the secondary, okay, till the neutral point, right? So this will be the V phase of the secondary. You can clearly see there are two windings which are coming here, A3, A4 and C1, C2. Okay, so that we have already seen that. Finally, the line voltage will be this voltage, right? So this is VL of the secondary side. So this is the various line and phase voltage. This, I think I have not put them in the previous diagram. Of course, I have explained the concept, but this is the better way of putting it. Now, to find all these things, we have to draw the basic vector diagram, right? So let us take this diagram to the next page and let's draw the vector diagram just how we drew for the delta star, and now we will draw for the star zigzag star. Okay, so let's copy it. I hope it was copied. Yeah, so it was copied finally. Now let us draw the vector diagram. Now the star side, let us draw the star vector diagram on for the primary side, sorry. So the primary side, the vector diagram will look like this. Very simple. So this is the A phase. So I am taking the dotted polarity, right? So this is A1, A2. This will be now A2, B2, C2 are connected together to form the neutral, right? So this point will be the same. So this is B2, this is B1, and finally this is C2 and this is C1. So the balanced three-phase supply here. So this vector will be VA1, V2 phasor, and this will be VB1, B2, and this will be VC1, C2, right? So this is the star side phasor diagram. Now let's draw for the secondary side. So we start as usual. We just we'll get the same diagram as we saw in the first case of the delta zigzag star. For the secondary side, we'll get the same phasor diagram, but let us draw it once again. Clearly see A1, B1, C1 is taken as the neutral side, right? So we'll draw the phasor diagrams for VA2A1, VB2B1 and VC2C1. So that is the phasor diagram that we are going to draw. So let us put this point here, and this is the neutral point A1, B1 and C1. So let's start with A1 here. So this is A1, and I have already told you if this is A1, A2, right? So this will be A2, A1. Okay, this is basic vector concepts. So we are going to draw VA2A1, VB2B1 and VC2C1. So VA2A1 will be in the downward direction like this, right? So these two are 180 degree out of phase. So this is VA2A1, right? And VB2B1 let us draw now. So that will be 180 degree out of this vector. So this will be B2 and this will be your B1, right? And so I can just draw like this just to show that these are 180 degree out of phase. And C2, C1, I can draw it here now. It will be 180 degree out of phase with this. So this is C2, C1 in the primary side. So this will be the C2, C1 in the secondary side, because we are measuring the voltage at the other side. So this is C1, C2, this is C1, this is C2, therefore this will be C2 and this will be C1. Okay, basic concepts. So this is sorry, one second, I just put it as B1. This is B1, this is B2, this is C1 and this is C2, right? There's no other mistake here. So this is A2, B2, C2 vector diagram we have drawn, okay, for the secondary side. So this will be 3 dashes and we can draw this here as well, okay. So now we have drawn for VA2A1, B2B1 and C2C1. Now let us see the connections and complete the vector diagram. So now A2 is connected to B4, right? A2 is connected to B4. Therefore, A2 and B4 are at the same potential, right? They are equipotential. So I'll just draw B4 here, somewhere around here. I'll just mark B4, use a different color. So what vector we have to draw? Now clearly, I'm taking the output across A3, B3 and C3. So the vectors I will be drawing for the B phase will be B3, B4, A3, A4 and C3, C4. Because I'm taking the voltage outputs across A3, B3 and C3. So those will be the higher polarity and that are reference with respect to A4, B4 and C4. So the vectors we are going to draw now are VA3A4, VB3B4 and VC3C4. Okay, so this B4 already I have identified and I have to draw B3B4. So B3B4 clearly see this is the dot polarity. So we are taking at the same point. So that vector and this B phase vector will be exactly in phase, right? Both are in the same dot polarity. Input is applied to dot, output is taken across dot. Okay, so let us draw the vector parallel to this vector. So this will be B3. So this vector will be V, BV, B3, B4, right? This is vector V, B3, B4. Let's take the second connection now. B2 is connected to C4, right? B2 is connected to C4. The B2 and C4 are equipotential. So I'll just put C4 somewhere around here because these 2 points are representing the same things. And that C3, C4 will be in phase with this vector C1, C2. Okay. So that will be in phase with this vector C1, C2. Okay. So this is C3, C4, right? So I will just mark that points here. So this 2 dash, this also 2 dash, just to show that these two vectors are parallel. So this has 3 dash, usually C phase I put 3 dashes. So this is 3. So these are 2 in phase. Now the final connection is between C2 and A4, right? C2 and A4 are connected. If C2 and A4 are equipotential. So C2 and A4 are the same point, right? C2 and A4 are the same point. So what is the vector that we have to draw? We have to draw C3, C4, right? Sorry, we have to draw not C3, C4. We have come out like this, right? So we have to draw the vector A3, A4 now. So A4 I have already marked and now I have to draw A3, A4. Now, A3, A4 is parallel to or in phase with A1, A2, right? Clearly it will be in phase with A1, A2. The thing here is that the primary vector A1, A2, if you take like this, that will be in phase with A3, A4 as well as A1, A2. But here we have taken A2, A1 because A1, B1 and C1 were taken as neutral. Okay, anyway. So let's draw the A3, A4 vector which will be in phase this vector which is A1, A2. So this will be A3, A4. Right, A3, A4. Now with this, we have drawn the phasor diagrams as such. So now it's time to find what is the phase voltage. So what is the phase voltage? It is the voltage from one phase to the neutral point. So this is the outputs, right? A3, B3 and C3. So the phase voltages will be A3N, B3N and C3N. So we have to identify that positions in this vector diagram. So A3N, where is A3N? Yeah, this is A3N. Right? So this will be VA3N, right? Where is B3N? So this is the neutral point, right? Remember that A1, B1, C1 are connected to become the neutral point. So this is VB3N, okay, and the C phase will be this vector here, right? So this will be VC3N, right? Now we have not found out the equation for this, but for now we have done the phasor diagram, and this is very important in identifying the equations which we are going to find out. That is the phase transformation, sorry, the line transformation ratio. So let's take it to the next page here. And let us find out the equations. Now, the equation for what do we want to find? We want to find the value of, so this didn't come, right? So VA3N. Okay. So we want to find what is the value of VA3N, right? So VA3N will be the vector sum of this vector, which is VC1, C2, right? VC1, C2 plus this vector here, which is VA3, A4. So it's not C1, C2, it is C2, C1, because C1, A1 and B1 are the neutral points, right? So sometimes I just gets mixed up with the words. So anyway, it is VC2, C1 plus VA3, A4. So now the thing is, what is the magnitude of VC2, C1 and what is the magnitude of VA3, A4? So that is the basic understanding that we need. So for example, now this is the line voltage which we are applying, right? So we'll just find out those values here. So now if V phase of the primary side, because it's a star connection, which will be equal to VLP divided by root 3, right? Why? It is because of star connection at the primary side. Now that entire voltage, if the transformation ratio is K, that entire voltage will be equal to, will be transferred to the secondary. That entire voltage will be K into V phase of the primary, or K into VLP divided by root 3. But here I told you in the zigzag connection, each winding is divided into half, right? 2 halves. So the total voltage will get divided into 2 here. Therefore, if you take the V phase of the secondary side, that is this voltage here, V phase of the, not V phase of secondary, that is, we have to find it later. That is the value of V, what was the value that we had to find? VA3A4, right? So VA3A4, which is one set of the one half of the winding, that will be same as in magnitude of C2, C1. Both will be exactly the same because the transformer is identical, 3-phase balance supply. So the magnitude will be exactly the same. So that will be equal to K into V phase of the primary divided by 2. Okay, right? K into V phase of the primary is the total voltage transferred, but here the windings are divided into 2. So each winding will get half of the voltage, right? So this value will be equal to K into VLP, right, divided by root 3 divided by 2. Okay, so this is the value that we need, right? So we'll write that here. So that these two values are equal, so it will be K into VL divided by root 3 divided by 2, right? Divided by 2. Yeah. Now just like how we derived for the delta zigzag star connection, we can use triangle law of vector addition and we can find the value of VA3N. So this angle is 60 degrees. If you do a little bit of trigonometry, you will find that the angle between A3 and A4 is 60 degrees. This vector and this vector, that is the angle between VC2, C1 and A3, A4 is 60 degrees. So the magnitude of VA3N will be equal to root of, I'll just write down the formula, C2, C1 square plus VA3, A4 square plus 2 into VC2, C1 into VA3, A4. Of course, everything is in magnitude, multiplied by the cos of the angle between these two, and that angle is 60 degree. So I'll just put that 60 degree here. And what is the value that we have already found out here? C2, C1 is K into VL divided by root 3 divided by 2 the whole square plus A3, A4 is also the same value, K into VL divided by root 3 by 2 the whole square. I can put that VL primary, right? I'll just put VL primary here so that we have a little bit more clarity, plus 2 into K into VLP divided by root 3 divided by 2 multiplied by the same value k into VLP divided by root 3 by 2 into cos 60 degree. Cos 60 degree. So if you simplify this, if you do a little bit of simplification, you can find that this cos 60 is 1 by 2. So this 1 by 2 and this 2 will get cancelled. So ultimately you will get k into VLP divided by root 3 by 2 the whole square plus k into VLP divided by root 3 by 2 the whole square plus, because this 2 and this cos 60 goes, this value will be equal to k into VLP divided by root 3 by 2 the whole square, right? So this value here will be equal to root of 3 times k into VLP divided by root 3 by 2 the whole square, right? So V magnitude of VA3N is this value here. So we can do a little bit of further simplification of this. So finally we will get root 3 for this 3 here, and this entire term is under the square root, so it will just come out. So this will be root 3 into VLP, right, divided by root 3 into 2 into k. Yeah, so now we can just simplify it. So finally we will get VA3N will be equal to k into VLP divided by 2. So that is what you get here. Okay, k into VLP divided by 2. But we want to find the line transformation ratio, right? But here if you divide these two quantities, you will not get line transformation ratio. So because this is a star connection and this is nothing but, this VA3N is nothing but the phase voltage of the secondary side. So the line voltage of the secondary side will be root 3 times V phi s, right? Because it is a star connection. Even though it's a zigzag star connection, ultimately it is a star connection, and because the voltages are 3-phase balance voltage, you can use those equations. So this value will be equal to VLS will be equal to root 3 into V phi s. V phi s is this value, so it will be equal to root 3 into k into VLP divided by 2, right? So I can just write the line transformation ratio from here. So VLS divided by VLP, line voltage of the secondary divided by the line voltage of the primary, is equal to the line transformation ratio, and this value is equal to root 3 by 2 into k, right? So if the transformer that you have had is having a transformation ratio of k, when you connect it in a star zigzag star connection, the transformation ratio will be root 3 by 2 into k. So that is the basic conclusion. So now you have found out the equation, right? So this is the equation that we have found out. I hope there was no confusion here. Now let us see the vector group thing here. So vector group, again you can use the vector diagram. I think it is still there. I'll just paste it. Oh, something else came there. So let's take this vector diagram once again. Yeah, so I'll just copy this here to draw the compare the vector group. Okay, yeah. So you have the primary side and you are having the secondary side here. Now the primary phase voltage you can see is this thing here, right? So this is the primary A phase phase voltage. Okay, so this is the primary side. So secondary is this one. So secondary is this one. So if you compare these two together, this will be VA1A2, right? And this value here will be VA3N. Right? This is the phase voltage of the secondary side. Okay, and this angle is 30 degree. If you do a little bit of trigonometry here, if you just draw a line here, you can find that this angle is 30 degree. Now what type of connection is this? You can clearly see the phase difference. The phase difference between these two voltages, is, so in the clockwise if you take, this is minus 30 degree. Always clockwise angles are positive and anti-clockwise angles are clockwise angles are negative and anti-clockwise angles are positive in electrical engineering. So this will be this minus 30. So the clockwise it is minus 30. Now, so therefore this connection you can call it as a star Y, right? For the capital Y for the primary star connection, and the small z for the secondary zigzag connection, and how much is the angle? Minus 30 degree, right? Or with respect to clocks, this will be 12 o'clock and this will be 1 o'clock. Always the primary voltage is taken as the 12 o'clock, right? So this will be YZ1 connection. YZ1 connection. Just it looks like the star delta or delta star connection. In star delta and delta star connection also you had found minus 30 degree or plus 30 degree, etc. Okay, so today we have just started with the star zigzag star connection. I hope you have understood this. If you are having any doubts, please put them in the comments below, and please do like, share and subscribe to the channel if you have liked this video, and please do recommend these videos with your friends, because the vision of this channel is to bring such videos to a larger audience. Unless you share these videos, it won't be possible. Please tell them that there are other courses in this channel like engineering circuit analysis, DC machines, as well as synchronous machine and transformers is running on. So till I see you in the next video with the next configuration of the star zigzag star connection, is me Varun signing off, and have a great day. Thank you.